Hi everyone, my name is Big Patana Montong Tanunam. I'm a lecturer at the University of Melbourne, and today I'm very glad to be invited to present a meeting keynote at MSR 2021. And in this talk, I will give some highlights about how data mining can help developers do code review faster. So just a quick introduction of code review. Code review is a quality assurance practice that is performed before or at the same time as testing in the development cycle, and it is a practice that manually examines every new code change to ensure the overall quality. And several studies have shown that code review has provided many benefits, including improve the quality of the code change or the system, or even improve the team collaboration, which is increasing team awareness or knowledge transferring. However, unlike the other QA practices, code review requires a lot of human effort since it is mainly a manual work. And as you may know, the modern software development creates a large number of code changes. Hence, it is very challenging for developers to carefully and effectively perform code review for each code change given a limited time frame. And today I just want to point out two main challenges in the code review process and how can we help them. And the first one is non-responding invited reviewers. So if we look into the code review process here, it is unlike the traditional software inspection where teams will properly set up the meeting for the review. In the modern code review process, there relies more on the participation, and when the code author sends a review invitation through the code review tool, it is possible that some reviewers may not respond to the review invitation. And indeed, we find that about 16 to 66% of the studied code changes have at least one invited reviewer who did not respond to the review invitation or didn't participate in the code reviews. Based on this, we want to further understand what are the factors that can be associated with the participation decision of a reviewer. Therefore, we did a statistical analysis to investigate which factors could be associated with this decision, and we used 13 metrics in this study, which are grouped into 3 dimensions, which are experience and activeness, the past collaboration, and the workload of reviewer. And from our data analysis, we found that there are 5 significant factors that could be associated with the review participation decision of reviewers, and 3 of them are from the experience or the activeness of the reviewers. 1 of them is from the past collaborations, and 1 of them is from about the workload of the reviewers. So based on these findings, we then develop a workload-aware recommendation, or workload-aware reviewer recommendations, our approach to help them to do a code review faster. And basically, in our approach, we use a multi-objective evolutionary search or the search-based algorithms to consider all of these 5 significant factors to recommend a set of reviewers that best satisfy the 2 objectives. And the 2 objectives here is to maximize the chance of participating a review or reviewer while minimize the skewness of the workload. In other words, we want to make sure that when we invite the reviewers, the workload will be equally or fairly distributed. And when we compare our approach with the single objective approach, we found that our approach outperformed the single objective approaches, and this highlights the benefit of using the multi-objective search-based approach, and also highlight that the considering of the workload distribution of reviewers when recommending a reviewer helps a lot when we find a new reviewer for a new patch. So this is our first challenge, and the one possible solutions. And the next challenge is the suboptimal reviewing. In this aspect, there are actually many forms of suboptimal reviewing. And recently, we just found one more, which is a potential of a subconscious bias of reviewer. In particular, in the modern code review tools, they provide a transparent environment where everyone can look and at the code change or the code reviews, and it is possible that they might use such visible information other than the patch itself to consider whether or not this patch should be accepted. And in this example, the first one is like I am the reviewers, and then I can see Ahmed names as an author, and I have worked with him for a long time. I may have some bias and feel that he might need a good job on writing the code, and then I just approve. Another possible way is that when a newly joined reviewers come into the code review tools, they can see the other people feedback, and if the feedback is already positive, the reviewers might perceive that the patch is already good, and they did not give a careful review. So based on this, we conduct a data analysis to analyze the association between the visible information other than the patch characteristic and the review decision of reviewers. And we find that the visible information such as the relationship, the status, and prior feedback has a stronger relationship with the review decision of a reviewer more than the patch characteristics. So these results suggest that despite the conventional wisdom that a new patch should be solely evaluated based on the technical merit, we find that the visible information has a stronger relationship with the review decision of a reviewer. In addition to the subconscious bias, there are many other suboptimal reviewing practices that could exist in the code review tool, such as the low review participations, or they joined the review but did not provide much comments. There is confused reviewers who do not understand the rationale and understanding the code. There could be the divergent reviewers, there could be some shadow reviews, and there could be some toxic reviews. So based on these findings that we have done so far, we think that it would be good to help them to reduce their effort by highlighting the lines that are likely to be defective in the futures. We did this because when we do analysis, we found that in the source file, there is only 1 to 3% of its lines are actually defectives. So we believe that predicting defective lines would potentially save reviewer effort on inspecting the code. And the idea of our approach is actually quite simple. We use a model agnostic approach or an explainable AI technique to explain the file level defect prediction model, explain which lines in the source files is likely to be defective. So if you look into this example, we given the source file, and our file level model says that this file is likely to be defective. We use the alarm, which is an explainable AI technique, to say which token in this code is likely to be defective, is a risky one, and then we map into the line. Based on this approach, we compare with the other approach like static analysis tool or the Ngram, and we find that our approach achieve overall performance better than this baseline approach. So, based on these two challenges and two possible solutions, we believe that they can help teams to speed up the code review process and save the human effort while maintaining the quality of the reviews. Nevertheless, I believe that there are still many challenges exist and needs us as a researcher to help. So if you have any other good idea or looking for the collaboration, feel free to contact me. I'm very happy to work with. And finally, the talk today is just a very short introduction of my work and with my collaborators. If you are interested in the details, please feel free to go and check our papers. And if you have any questions, please do not hesitate to contact us. Thank you.